हेलो फ्रेंड्स, मेरा नाम अनिल है एंड आई एम सॉफ्टवेयर इंजीनियर बाय प्रोफेशन। मैं अभी लंदन में एज ए बैकएंड इंजीनियर काम कर रहा हूँ और इससे पहले मैंने बैंगलोर में फ्लिपकार्ट में एज ए SD2 बैकएंड इंजीनियर काम किया है। बट मुझे पढ़ाना अच्छा लगता है, सो आई एम जस्ट स्टार्टिंग माई न्यू यूट्यूब चैनल वेयर आई विल टीच मैथमेटिक्स टू द स्टूडेंट्स। सो आज अपन चालू करते हैं टेंथ NCERT चैप्टर 1 रियल नंबर से। सो हम इस चैप्टर को एकदम डिटेल में स्टडी करेंगे एंड होपफुली यू फाइंड इट हेल्पफुल। सो आराम से इसको धीरे धीरे 1 बाय 1 देखते हैं, लाइक सारे सेक्शंस को। लाइक आई बिलीव कि अपनी जो NCERT की बुक है दैट इज़ सफिशेंट इनफ टू क्रैक और लर्न इनफ कंटेंट। सो हम इस पे फोकस करेंगे, लाइक व्हाट इज़ द कंटेंट ऑफ NCERT, एंड उसी के एग्जांपल्स को सॉल्व करने की कोशिश करेंगे। सो लेट्स स्टार्ट। सो इंट्रोडक्शन में हमें दिया है लाइक you began your exploration of the world of real numbers and encountered irrational numbers. We continue our discussions on real numbers in this chapter. We begin with two different important properties of positive integers, namely Euclid's division algorithms and fundamental theorem of arithmetic. So real number क्या है actually? So रियल नंबर को हम इस तरह डिफाइन कर सकते हैं, विच एग्जिस्ट इन रियलिटी। सो लेट्स से अगर हमें कोई नंबर लाइन दिया है, एनी नंबर लाइन इज गिवन एंड ये 0 है। सो ऑल द नंबर्स विच कैन बी रिप्रेजेंटेड ऑन दिस नंबर लाइन आर कॉल्ड रियल नंबर्स. So let's say it can be whole number like 1, 2, 2, 3, like these integers, and between these integers there can be a decimal numbers as well. Let's say 0 to 1 के बीच में 1/2 हो सकता है, 1/3 हो सकता है, and it goes like infinitely many numbers. Then similarly you will have numbers on the negative side of 0, like left side of 0 will be negative numbers, -1, -2, these are integers. And again, like there can be -1/2 between 0 and -1, and this will go till infinity. And it also includes the rational numbers. So rational numbers तो यही हो गया, like any number which can be represented in fraction p/q where q not equal to 0. So this is called rational number. Even 2 can be represented as fraction, like 2/1. So this consists of rational as well as irrational numbers. So what are irrational numbers? Irrational numbers उनको बोलते हैं which cannot be represented in the form of p/q. ओके, सो अगर इस फॉर्मेट में नहीं लिख सकते तो दोज आर कॉल्ड इरेशनल नंबर्स, बट स्टिल दे आर रियल नंबर्स, बिकॉज हमने 9th में देखा था कि वी कैन रिप्रेजेंट a real irrational number on this number line. So we had drawn a line, like let's say take a line of 1 unit from here and you make 1 unit from here. So ये जो डिस्टेंस है that will be √2. like if this is 1 unit and this is 1 unit, this will be √2. ये क्यों हो रहा है? like Pythagoras theorem से like c² is equal to a² plus b². so c² is equal to 1² plus 1² मतलब 2. so c की वैल्यू क्या हो जाएगी? √2. एंड √2 हमने देखा था दिस इज irrational number. It cannot be represented in the form of p/q. इसका प्रूफ हम इस चैप्टर में देखेंगे, बट हमने देखा है, लाइक 9th में स्टडी किया था कि दिस वैल्यू विल बी irrational and that is √2. so if we take this length and try to plot this on number line, let's say ये 1 unit है, ये 1 unit है, and if you try to plot, So root 2 will lie somewhere else on the number line. So that means like these numbers also can be represented on number lines. So these are called real numbers. Why do we call it real numbers? Because there are imaginary numbers as well, and imaginary numbers also have great significance in mathematics, but it is beyond our scope. Let's say, just to give the glimpse of what imaginary numbers are, uh, uh, let me give an example. So what about the square of any number? Can it be negative? So uh, let's say I am taking -1. The square of -1 will be 1. Square of 2 will be 4. Square of -2 will be 4. So any square number will be positive, like greater than equal to 0. Like 0 square will be 0. 1 square -1 square. You take any number, its square will be greater than 0. So uh, uh, let's say, imagine a number whose square is not equal to 0. So in mathematics we have a concept like this. Uh, we have iota, and it is represented as square root of -1. So अगर इस नंबर आयोटा को अपन स्क्वायर करें, सो इट विल बी माइनस रूट इंटू -1 root, so it will be -1. So this is imaginary concept, like it doesn't make sense and it cannot be represented on number line. But to deal with imaginary numbers, we have a concept like there exists a value called iota, which is the square root of -1. So means like iota square value will be -1. This is not possible in real life. So that's why these numbers are called real numbers and other numbers are called imaginary numbers. But imaginary numbers is beyond our scope, so we will leave it here and move ahead. So there is Euclid's division algorithm. And what is Euclid's division algorithm states? Let's take an example and see. So given two numbers a and b, a greater than b or equal to also is valid. Uh, this this greater than equal to is not required, because irrespective of this, these two numbers can be written in the form of a is equal to b into q plus some remainder r. Okay, so let's take example of 5 comma 2. So this can be represented as 5 can be represented as 2 into 2 plus 1. So a is 5, b is 2, q is 2 plus remainder is 1. So this is called Euclid's division lemma. Okay, so if you notice, it's the same division which we have been performing or learnt since our like earlier classes. We follow the exact same statement, but we formally write it as like this: a bq plus r, where value of r is less than equal to b. और ये लेस देन इक्वल टू बी क्यों होगा? बिकॉज अगर इफ लेट से आर वॉज इक्वल टू बी नहीं होगा, इट हैज़ टू बी लेस देन बी, बिकॉज अगर आर इक्वल टू और उससे बी से बड़ा होता देन ये एक और बार डिवाइड हो जाता. लेट्स चेक लाइक दिस. 5 कैन बी रिटर्न एज 2 into 1 plus 3. Correct. This can be written as 2 into 1 plus 3. यहाँ पर क्या हो गया कि रिमाइंडर इज ग्रेटर देन 2, लाइक रिमाइंडर इज ग्रेटर देन बी. तो अपन इसको फर्दर डिवाइड कर सकते हैं. लाइक 3 को कैसे लिख सकते हैं? 2 plus 1. करेक्ट. 2 plus 1 लिख सकते हैं. सो यहाँ पर अपन देख रहे हैं तो 2 plus 2 plus 1. So this 2 can be rewritten as 2 times 2 plus 1. तो यहाँ पर आपने देखा कि अगर ये इससे बड़ा होगा तो we can always divide this number one more time, like more than one time, and represent in the form like this, where b will be lesser than, always lesser than, sorry, remainder will be always lesser than b. So this is Euclid's division statement. And this is like it has very wide application, so this is very important to understand. uh, it's it's also written as like this. Dividend is equal to divisor into quotient plus remainder. अभी चलते हैं आगे, like what is it has to say. So one of the application of this division, Euclid's division algorithm is finding the HCF of two positive numbers. We'll see how we can use this concept to find the HCF of two numbers. The fundamental theorem of arithmetic, on the other hand, has to do something with multiplication of positive integers. You already know that every composite number can be expressed as product of primes in a unique way. This important fact is the fundamental theorem of algorithm. हमने शायद अर्लियर क्लासेस में देखा होगा कि एनी नंबर कैन बी रिप्रेजेंटेड एज अ प्रोडक्ट ऑफ प्राइम numbers, like prime factors we can say, and that factorization is unique. If we consider the order of primes in which they multiply, if we don't consider that order, so the factorization is always unique for a number. We'll see the examples and understand it better. And this has very deep significant application in field of mathematics. Again ये भी काफ़ी important है. We use the fundamental theorem of arithmetic for two main application. First, we use to prove the irrationality of numbers like √2, √3, √5. Second, we apply the theorem to explore when exactly the decimal expansion of a rational number, say, is terminating and when it is non-terminating. You will see that prime factorization of q will completely reveal the nature of the decimal expansion of p by q. So like rational number की definition क्या थी? Like it can be represented by in the form of p by q where q not equal to 0, and when we try to write in decimal forms, it takes the two form. Either it will terminate or it will not terminate, but it will start repeating after some time. So that means like those numbers can be represented in the form of p by q, and it doesn't, if the decimal representation doesn't terminate, it keeps on repeating. Okay, some irrational numbers like pi, they don't repeat also, and they don't like terminate also. But here we will see how we can use this fundamental theorem of arithmetic to analyze which fractions p by q decimal representation will eventually terminate, or if it doesn't terminate, then where where it will start repeating, like how it will start repeating. So this analysis can be done. Sorry if I mentioned pi as rational number. So pi is irrational number. So any number which cannot be represented, like which cannot be represented in this form, like p by q, which is let's say uh, non-terminating, non-repeating, those will be always irrational numbers. Euclid's division lemma. लेमा का क्या मतलब है? Like lemma, I think it means like it's a proven statement which can be used to prove other statements. So let's take an example. They have given an example here. A trader was moving along a road selling eggs. An idler who didn't have much work to do started to get the trader into a worldly duel. This grew into a fight. He pulled the basket with eggs and dashed it into the floor. The eggs broke. The trader requested the panchayat to ask the idler to pay for the broken eggs. The panchayat asked the trader how many eggs were broken. He gave the following response. So, like, इसका क्या मतलब है? Like, there was a basket full of eggs and it got broken. So उसे पूछ रहे हैं कि कितने eggs थे basket में, so that the idler can pay for that. So वो बोलता है कि if counted in pairs, one will remain. In counted in threes, two will remain. Fours, fives, four will remain. Six, five will remain. Like similarly, if counted in seven, nothing will remain. My basket cannot accommodate more than 50 eggs. तो इसको समझते हैं क्या बोलना चाह रहे हैं. So if you see कि there was a basket full of eggs. So basket full of eggs, and this basket, sorry, this basket cannot have eggs more than 150. So like number of eggs is less than 150. Cool. अब बोल रहा है if counted in pairs of 2, so one will remain. So number of eggs, let's say number of eggs is e. Number of, sorry, number of x is e. So e can be represented in this form, 2x plus 1, and in counted in pairs of 3, 3y plus 2. So in counted in the pair of 3, there will be remainder of 2. Similarly, if counted in pair of 6, 5 will remain, and in counted in pair of 7, 0 will remain. 7p plus 0. That means like 7 is completely dividing e. So हमें क्या करना होगा? Like we have to start like the trial and error विथ द वैल्यू ऑफ ई. तो ई की वैल्यू क्या क्या हो सकती है? सिंस इट इज़ कम्प्लीटली डिवाइडिंग, like it is completely divisible by 7, so e can be something like 7, 14, 21, 28 से लेके कहाँ तक जा सकता है? लाइक डिवाइड 150 बाई 7, 7 टू जा 14, सो ये क्या हो सकता है? 10. तो 7 टू द 14, फिर 1 बचा 10, 7 1 ज़ा 7 and remainder will be 3. So it will be always less than 150. So what can happen? That like last number where we can go is 147. You multiply 21 into 7, you will get this 7 to the 14 plus 7. So ये सारी possibilities हैं E, and then we have to try to find a number where these equations will be satisfied, like these conditions will be satisfied. So if you do that trial and error, I think you will get answer as, okay, it will be 119x. So you are also getting back to the puzzle. Do you have any idea how you will solve it? You must look for the multiples of 7 which will satisfy the condition by trial and error using the concept of LCM. You will find he had 119x, correct. So like let's see 119x, how it will satisfy this condition. So let's say e is equal to 119. So is it a multiple of 7? So if we see 119 divided by 7, 7 1 then it has 49, 7 7 49. So 17 times 7 is 119. So this condition holds true. Now let's see if it is divisible by 6 and leaves the remainder 5. So 1119 can be represented as 6z plus 5. So if we subtract 5 from it, it will leave 114. Now let's see 114 should be divisible by 6. So if you take 6 here, so 6 1 6 and it will leave 54. So 6 9. So if it divides by 19 times, yes, so it will be 19 here. So it can be represented as something like this. One 119 can be 7 into 17. 119 can be 6 into 19 plus 5. Similarly 119 can be represented as 5 into some value q plus 4. So 119 minus 4 is equal to 5q. 1115 is equal to 5q. And if you see 5 2 ja 10 and 5 3 ja, so it will be 1119 can be represented as 5 into 23 plus 4. Similarly, you can check for other conditions, it will satisfy all the conditions. So the answer in this case will be 1119. Now let's look at other things. So in order to feel for what Euclid's division lemma is, consider the following pairs: 17 6, 5 12, 20 14, 24, 20 and 4. So 17 can be written as 6 into 2 plus 5. 6 goes into 17 twice and leaves the remainder of 5. Similarly, even यहाँ पर देखो 5 is lesser than 12, but still it can be represented in this format, like 12 into 0 plus 5. And here 4 into 5 plus 0. Here 4 completely divides 20, so remainder is 0. So by now you must have understood like what this representation means, like how two numbers can be represented in this form, and two numbers can be uniquely represented using this particular division lemma. So there is some exercise, like you can try finding the integers q(n) for the following pairs. So ये इजीली हम देख सकते हैं, like let's say for 10 and 3 का हमें चेक करना है, तो how you will do that. So let's say 10 can be represented as 3 into 3 plus 1. So यहाँ पर q will be 3 and r will be 1. Similarly 4 can be represented as 19 into 0 plus 4. So यहाँ पर quotient is 0 and remainder is 4. And similarly this 81 is completely divisible by 3. So 3 2 is 6, 21, 27. Quotient q is 27 and remainder is 0. So we can move ahead. So like this is a formal statement of Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying this equation. So you can remember this particular statement, and this is called Euclid's division lemma. Then there is some historic background here. So it has been known for a long time, but it was first recorded in the Euclid's algorithm book. And then there is interesting fact about this, the word algorithm, like what it means and who coined it, called Hisab algebra by Muhammad ibn Musa, and it was like 780 to 850 CE. A lemma is proven statement used for proving another statement. Yes, I was referring to this particular statement. Lemma is called proven statement used for proving other statement. Euclid's division algorithm is a technique to compute the highest common factor. So हमने पिछले क्लासेस में देखा होगा, like 9th standard में. So there also we used to find the HCF of two numbers, but that was using prime factorizations. यहाँ पर there is different approach, and it's a faster approach to find the HCF of two numbers. And what this approach says, like given two numbers 455 and 42, find the HCF of these two numbers. So how do you find it? Like अगर हमें without Euclid's lemma find करना है, तो how we will do this? So what were the numbers? I think 455 and 42. Yes. So we can see, like given two numbers 455 and 42, like find HCF of this HCF. So how you will do this? Like you will do the prime factorization of this. So I know, like this will be division 1 by 5, because like n digit is 5. So 5 can be written as like this 455 can be written as 5 into 5 9 the 45 and 1. So 5 9 the 45, and then there is like 5, right? It can be written as like this. And 5, it can be again broken down into something like let's say 7 1s are 7. So 7 into 7 1s are 7. Okay. And the remainder is 221. So we can write it as like 7 into 20, 7 into 21. So no, let's say 91 divides 7, yeah, 13. So 13 times, let me clear this. So it can be written as 13 times into 7. And if we do for the 42, 7 7 6 are 42. 7 into 3 into 2. So if you see, like 42 can be represented as a product of prime factors 7 3 2, and 4 4 4 5 5 can be represented as prime factors of 5 7 13. So what is the common factors between these two numbers? It's 7, and there is no other common factor. So HCF of these two number is 7. Okay, but here we have to, let's say, do the prime factorization of each numbers and try to find the common factors with the two. So we take all the common factors, and that becomes the HCF. That is the actual definition of HCF as well. But how it is done using Euclid's division lemma, let's see. So what Euclid's division lemma says, like given two numbers, you do the continuous division with the quotient and remainder. So let me explain it with example. So given two numbers, let's say 455 and 42. So 455 into 42 can be represented as this. So 455 minus 420, it will give 35. So this can be represented as this number. So basically, like, we are trying to write it in Euclid's division lemma form. Like, we divide 42 and try to write it in this form. Then what we have to do next is, like, until this remainder is 0, until this r becomes 0, r not equal to 0, we have to continue this division. But in the next step, we have to take 42 as a. So I'll write here a equal to b cube plus r. So our quotient will become a in the next step, and then our remainder will become the b in the next step. So 35 into 1 plus something we have to write. So 42 minus 35, how you will write? 3 and 7. So you write 7 here. Again, this is not 0, so we move ahead. So next time a will become 35 and remainder will become b. So 7 into 5 plus 0. Now remainder has become 0. So that means this particular b here in this step is the HCF. This will be HCF of these two numbers. And why does it happen? Like, ये ऐसा होता क्यों? Like, why this number is HCF? बुक में ये ऐसे बोलते हैं कि HCF of two numbers a comma b, let's say a is greater than b, given two numbers, अगर कोई भी दो नंबर है, let's say in this case 225 and 135. अगर इसको उल्टा दे दिया 135, 225, तो लाइक एनी डे वी कैन रीअरेंज and this can go here. It doesn't matter like HCF two numbers A और B क्या है, it doesn't matter like उनका HCF like सेम ही होगा. So HCF of A comma B is equal to HCF of B comma A. करेक्ट. सो कोई भी नंबर अगर पहला नंबर छोटा दिया है देन दूसरे नंबर से, तो वी कैन इजीली स्विच एंड मेक इट बड़े नंबर को ए रिप्रेजेंट कर दो, छोटे नंबर को बी. सो तभी वी कैन अप्लाई दिस स्टेप्स, राइट. वी कैन राइट द बिगर नंबर इनटू फॉर्म ऑफ दिस. करेक्ट. लेट्स से अपन ट्राई करते हैं कि इफ़ यू डोंट डू दैट वे, अगर इसी एग्जांपल में इफ़ द एग्जांपल वाज 42,455, इफ़ A is 42 and B is 455, so 42 can be represented as 455 into 0 प्लस रिमाइंडर कितना बचेगा 42. सो नेक्स्ट स्टेप क्या हो रहा है कि ये इधर आ जाएगा 455 और B ये ले लेगा, रिमाइंडर विल बिकम B. And again like we have reached the same state, so it doesn't matter like the order doesn't matter here. So why this happens, like HCF of AB is same as HCF of Q and R. तो यहाँ पर इन ये because of this statement this happens, like this becomes the HCF. So let's try to understand like HCF of 455 and 42 is same as HCF of इसको क्या है 42 and 35, 42 and 35, and it is same as HCF of 35 and 7, and HCF of 35 and 7 we know 7 times 5, so here 7. Like 35 can be represented is into 7 into 5 or इसका HCF, so it will be 7. So 35 and 7 HCF is same as 42, 35 HCF is same as 455 2 and 42 HCF. बट अभी भी वो इंट्यूशन नहीं मिल रहा है हमें, लाइक वाई इज दिस हैपनिंग. ओके, लेट मी टेक अनदर एग्जांपल लाइक वेयर आई कैन एक्सप्लेन और दिस इज मोर एविडेंट. 225 एंड 135 का HCF ट्राई करते हैं अपन. सो HCF ऑफ दिस टू नंबर, इसको कैसे लिख सकते हैं, लाइक 225 कैन बी रिटर्न एज, इसका डबल कितना हो जाएगा 270 हो जाएगा, तो 135 इंटू 1 प्लस समथिंग होगा 225 माइनस 135, ये कितना जाएगा 0. ठीक है, 190. cool. So 135 can be represented as again 90 into 1 plus 90, अगर इसमें जाएगा तो कितना हो जाएगा 45. again 90 can be represented as 45 into 2 plus 0. So यहाँ पर 45 will be our HCF. Okay, and like we can easily see like the using prime factorization also. 225 को अपन कैसे लिख सकते हैं? लेट्स से 5 इंटू कितना जाएगा ये? 5 4 ज़ा 20, 49. So it can be correct, right? 5 4 ज़ा 20. Let me divide by this. 225 divided by 5 4 ज़ा 20. 5 5 sorry 45. It will be 45 here. So again ये 5 से जाएगा. 5 into 9. 9 can be represented as 3 into 3. So this is prime factorization of 2. And similarly for 135 I know ये 5 से जाएगा, तो 5 2 जा 5 into 5 2 जा, again let's do quickly, 135 divided by 5 5 2 जा 10, 35 5 7 जा 5 6 the 35 7 the 35, yes 27. So 27 can be written as 3 into 3 into 3. So we can see like एक 5 पैर यहाँ से उठेगा and 2 3 पैर यहाँ से उठेगा. So again 5 9 the 45 is our HCF. So we have seen like through prime factorization and through Euclid's division algorithm. So 45 is the HCF. Now let's take a closer look at this. So how we can write this? Again 225 is written as 135 into 1 plus 90. Let's say if I say what is the HCF of 90 comma 90, it will be 90. So HCF of x comma x is always x, because ये खुद से तो like पूरा ही चले जाएगा ना. Like how we are trying to find HCF by using the common factors. ठीक है. So HCF is like highest common factors. Like बड़ा number रहेगा which can divide both the numbers, like the largest number which can divide both. So here let's say there is 10 also, like I can divide 10 also here and 10 also here, but 10 is not the HCF. I can divide by 9 also, like 9 is the number which will divide both, but still 9 cannot be HCF because it is not the highest. The highest will be 90 here. So let's take a case of 90 comma 45. So I know like 9 will divide this also and this also, 5 will divide this also, this also, but highest number which can divide both is 45 here. Okay, so if a number is a multiple of the second number, so that number itself will be HCF. Let's say here 45 into 2 is 90. Here there is no remainder, so 45 will be the HCF of this number. So any number, let's say y is a number which can be represented into p comma q. Okay, y is a number, so HCF of, let's say y comma p will be q, or HCF of let's say HCF of p into q is the number, right? So HCF of y comma q will be p, क्योंकि we know like it is multiplying exactly, then remainder will be 0. So in that case we have this property. So given two numbers x y, and if one number divides completely the other numbers, that will be HCF. This is very intuitive, like very intuitive, as if like take the case of 100 and 25. We know like 25 divided hundreds 4 times. So here there can the number HCF cannot be greater than 25 itself, and this is 25 is a factor of 100, so that means HCF is 25 itself. So imagine a case like if there was a number, let's say 25 here, so this number could have been written as like 220, 225 could have been written as 25 into some number x, and the remainder would be 0. So 25 will be the HCF. So we are trying to find the common factor, highest common factor between these two numbers. So what we are trying to do, so if let's say there was a number 225 and it is written as 25 sometimes number x, means 25 can be taken out as a common factor, okay, from here, and it will be the highest factor here because there won't be any other number which could be taken out from here. So let's say if the representation is of the form like this, a is equal to bx plus c x. So we will try to take common factors out from both the parties, like b plus c, and if there is some common factors between b and c, we will try to take that as well out. So when we take all the common factors out, this number becomes HCF. So let's try to rewrite this in the similar fashion. So let me use eraser. Okay, so this is represented as this. Now how can we write 135? Let's try to write 135 again. So I am writing 90 into 1 plus 45 into 1 प्लस 90. अब यहाँ पर ऑब्जर्व करो कि इफ़ इट वॉज समथिंग लाइक 0, अगर ये 0 होता ये नंबर, इंस्टेड ऑफ 45, if this number would have been 0, we could have taken 90 easily out from here. Like we could have written something like this into 1 plus 1, कुछ इस तरह लिख सकते थे अपन, and 90 will become let's say the shape of this. But since this number is not 0, we cannot take 90 out like this, correct? So let's try to rewrite it as further rewrite it as like this. I am bringing this into 1, so 90 plus 40 plus 90. Okay, now how can we rewrite 90, this 90? तो हाँ, अपन 90 को कैसे रिराइट कर सकते हैं? 45 इंटू 2, ये जो इस स्टेप में है, सो 45 इंटू 2, इसको अपन ऐसे लिख सकते हैं. देन अगेन 45 प्लस इसको फिर से हम 45 इंटू 2 लिख सकते हैं, 45 इंटू 2. सो हम वी आर ट्राइंग टू राइट इट इन सच अ फॉर्म कि हमें एक कॉमन फैक्टर मिल जा रहा है विच वी कैन टेक आउट easily from all the numbers. So in this case 45 can be taken out now. So 2 plus 1 plus 2, कुछ इस टाइप से. So now we can see कि 225 can be written something like this. So 135 is broken down like this, and still this was not 090, could not be taken out. So what we try to write, like we try to write this number in form of this number. Okay, और ये इस नंबर को ही इस फॉर्म में क्यों लिख रहे हैं, बिकॉज इफ़ वी कैन राइट 90 इन फॉर्म ऑफ दिस नंबर, देन ऑटोमेटिकली दिस 90 विल बी रिप्रेजेंटेड इन द सेम फॉर्मेट. सो नेक्स्ट टाइम लेट्स से कि ये अभी भी डिविजिबल नहीं होता, तो आई नो लाइक फर्दर 45 could be written in form of 90, और वो ऐसे चलते जाता. Hopefully this gives the intuition like why we are doing like this, why this holds true. And HCF of A comma B becomes a HCF of Q comma R. So ये इसकी वैल्यू इसके बराबर है. That means like we can still go on until we find the HCF, because this is equal to this. So next step में we don't care about this. What we care about is just two values, because of this statement, and further like it will go further till this point. So hopefully you have got the intuition or idea behind this, why it happens like this. Again, I'm stressing like we try to represent a greater number in form of this number, and I know like 35 and 90, the like I have to take some common factors out of this full expression, like full expression. So how do I take the common factor out? I'll try to represent this number in some form of 90, because if I try to do that, so next step, if it is like it is completely dividing, let's say 90 is completely dividing 135, so I can easily take 90 out from this. And if it doesn't divide, then whatever expression I will write for 90, this can be substituted here. So it happens the exact same here. So I'm trying to write 135 as this format, 90 into something plus 45, and in next step I'm trying to break the 90. So if I try to break the 90 here, the same like breakdown will be represented here, right? So you try to imagine it more, like 90 can be written at 45 into 2. Okay, and then 45 of course like will go into 1 times here, and then again that same 90 is here present, so again it can be represented here. Now we have common factor 45, which can be taken out from the entire expression. So this is the exactly like algorithm. So what is algorithm actually? So algorithm is actually very important. Since I belong to computer science backend engineering field, I know there are lots of algorithms, and entire computer works on algorithm. So algorithm is a set of defined statement which can be followed to arrive on some kind of result or conclusion. So these are like steps, instructions. So this step, like you do write it in the form of Euclid's division lemma, and then if r equal to d, r equal to 0, then divisor is the HCF of c and c comma d. And again, if r is not equal to 0, then you have to repeat the same process, considering q like quotient and remainder in the next steps. So you keep on doing these steps in a repeated fashion unless you get the result. So the set of defined statements are called, like defined instructions are called algorithms. So this is called Euclid's algorithm to find the HCF. So again, this is the same procedure, like this is greater than this number, so we will try to represent it in division algorithm form, Euclid's form, and since remainder is not 0, so we repeat the same step. Quotient will become A, remainder will become B, and we continue till this point. Now here remainder B is 4, and it goes into 6 times, and now the remainder is 0. So our HCF is 4 this time. So here again, like why this is holding true is same. HCF of this number will be equal to HCF of this number will be equal to, it will go continue till HCF of 24 and 4. So HCF of 24 and 4 is 4. So that's why it holds true. Euclid's division lemma and algorithm are so closely interlinked that people often called this division algorithm as also. Although, but yeah, lemma is like the representation. You can write that in form of like dividend is equal to divisor into quotient plus remainder, but that is not algorithm. Algorithm is set of instructions, defined instructions. So ये जो process है which we see here, this is called algorithm. This is called algorithm, which is using the Euclid's lemma. But it is so common that these are interchangeably used, but this is not the same. Like lemma is different from algorithm. Although Euclid's algorithm is stated for positive integers, it can be extended for all integers except 0, where b cannot be 0. However, we shall not discuss this aspect here. So it states like it holds true for negative integers as well, but we will not explore that in this part. It doesn't hold good if b is equal to 0. So that is worth noting. Euclid's division lemma algorithm has several applications related to finding properties of a number. We give some examples of these numbers. So show that every positive even integer is of the form 2q, and that every positive odd number is of the form 2q plus 1, where q is some integer. So given any two numbers a comma b, इसको देखते हैं like how we can prove this. Like every even number is of this form and every odd number is of this form. So let's try to see this. Given any two numbers a comma b, using Euclid's lemma, a can be represented as bq plus r, where r is less than b. Cool. So any a is a let's say a is any integer, like set of integers, any integer a, and let's try to take a number b equal to 2. So a can be represented as 2q plus r. So r की क्या क्या डिफरेंट वैल्यू हो सकती है? r हैज़ टू बी लेस देन 2. So r can be either 0 और r can be either 1. So a की possibility क्या क्या है? a can be represented as 2q plus 0, it means 2q, or a can be represented as 2q plus 1. इन दोनों के अलावा there is no other possibility. No other possibility because r can be only 0 and 1, because it has to be lesser than 2। अब देखते हैं कि इवन नंबर्स किसको बोलते हैं, विच कैन बी रिटर्न एज मल्टीपल ऑफ 2. So 2 can divide this number, right? So all the even numbers, so all the integers can be represented in two format. Let's say 2q and 2q plus 1. We have seen like these are the only possibilities. So any integer can be represented in this format, and all the even numbers has to be divisible by 2. So that means uh, this is not divisible by 2. Why? Like 2 can be taken out as a factor from this, but we cannot take 1 because 1 will never divide, like 2 will never divide 1. So all the even numbers will be of the format 2q, and all the odd numbers will be of the format 2q plus 1. क्योंकि ये इवन नंबर्स हैं तो इवन नंबर्स प्लस 1 will be always odd. So we have proved this. So you can see here like some integers greater than like I forgot to mention like it is given like positive integers, so we are talking about only positive integers. So Euclid's algorithm, using Euclid's algorithm we can write a in the form of 2q plus r, where r can be 0 and 1. So a can be 2q or 2q plus 1. If a is of the form 2q, then a is an even integer. Also positive integer can be either even or odd, therefore any positive odd integer is of the form 2q plus 1. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3. So again we have to show let's say any integer a can be represented as bq plus r. Let's take b equal to 4, so it will become 4q plus r. R will be set of 0, 1, 2, 3, right, because r is less than b. So these are the only possibilities. So let me try to write 4q plus 0, 4q plus 1, 4q plus 2, 4q plus 3, and so any integer can be written in this format only. Now let's say 4q, it is a even integer, but it can be written as 2 into 2q. So this is even integer. Okay, similarly 4q plus 2 also can be written as 2q plus 1. So 2 is a factor, so this is also even. Okay, and 4q plus 1, this is even, plus 1 will be odd. Okay, and this is even, we have proved here. So this can be rewritten as 4q plus 3 can be written as 4q plus 2 plus 1, and 4q plus 2 is even, we have seen here. So this will be odd. So given a number, any positive number a, it can take only these forms. Let's say if I give number 1, so 1 can take only these forms. Like 1 can be written as 0 into 4 plus 1. Given let's say 5 can be written as 4 into 1 plus 1. So this is taking this form. So any integer can be represented only in this form, 4 form. Out of this one and this one are even. So odd numbers can take only these two form, 4q plus 1, 4q plus 3. So we have proved that as well. Now let's take an example of a sweet seller has 420 Kaju burfis and 130 Badam burfis. She wants to stack them in such a way that each stack has same number and they take up the least area of the tray. What is the number that can be placed in each stack for this purpose? So एक stack like let's say एक box stack है. How do I explain this? Okay, so let's take we have 420 Kaju burfis and 130 Badam burfis, and there is a stack, एक box है. So ये बादाम का है and there is another box of the same size, ये काजू का है. अब कंडीशन क्या है कि ये बॉक्स में लाइक अगर x बादाम है तो दूसरे इसमें x काजू होने चाहिए. सो दिस इज द कंडीशन कि कोई भी एक बॉक्स में वी हैव टू हैव सेम नंबर ऑफ बर्फीज, लाइक आइदर इट कैन बी काजू और इट कैन बी बादाम. सो और हमें इसका एरिया भी कम करना है, लाइक वी वांट टू रिड्यूस द एरिया. वो तभी हो पाएगा व्हेन वी ट्राई टू पुट मैक्सिमम, लाइक x वी ट्राई टू मैक्सिमाइज x जितना बड़ा नंबर होगा उतना ही कम बॉक्सेस बनाने पड़ेंगे, राइट. सो इट्स लाइक we can rewrite it in some format, like let's say, let me tell. So what we want, x is the capacity of stack, capacity of stack. So we have to maximize x जितना बड़ा होगा उतना ही एरिया कम लगेगा. सो 420 कैन बी रिप्रेजेंटेड एज सम p into x, right, and 130 can be represented as some q into x. So x has to be maximum. So it is like x should be taken out as a common factor from 420 and 130. It's as good as finding the HCF of these two numbers. अगर is highest common factor is the number which divides both these two numbers, and that is x. So we want to find HCF of these two numbers. I can easily see here. Let me check, like 10 is the common factor of both 42 and 30. So 10 is taken out, and is 13 multiple of this? No. 13, 26, 39 and 52. So 13 is prime number as well. So there is no common, like there cannot be any factor of this 13. So there is no common factor. So 10 is the HCF of this two number. That means एक बॉक्स में हमें 10 बर्फीज रखनी है. ओके, सो दैट बादाम भी 10 हैं एंड काजू भी 10 है. तो बादाम के कितने बॉक्सेस बनेंगे? बादाम के आई थिंक इट विल बी 42 बॉक्सेस एंड इसके 13 बॉक्सेस बनेंगे. इन टोटल 42 प्लस 13 555 बॉक्सेस बनेंगे. सो 10 इज द आंसर. use Euclid's division algorithm to find the HCF of this. Again, like I have already taken this example. Similarly, you can find for these two numbers. Show that any positive odd integer is of the form this. So यहाँ पर again like you'll do the same approach. कोई भी इंटीजर्स को हाउ यू कैन राइट लाइक यहाँ पर बी विल बी 6, तो इट विल बी 6q. Let me write on this. Either it can be 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. इतनी पॉसिबिलिटी है हमारे पास. Now it will have factor like 2 into 3q. This will be odd. It will have again factor 2 into 3q plus 1. This cannot be written in form of 2. Again 6q plus 4, 2 can be taken out. 3q plus 2. Again here we cannot factorize it. So these are even numbers, this, and the remaining numbers will be odd numbers. You can easily prove that. Any contingent, an army contingent is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So army contingent of 616 members to march behind an army band of 32 members in a parade. Okay, the two groups are to march in the same number of columns. Okay, what is the maximum number of columns in which they can march? So 616, I think 616 and 32. तो 616 मेंबर्स को 32 मेंबर्स के पीछे चलना है. तो लेट्स से देयर इज लाइक कॉलम 1, कॉलम 2, कॉलम 3, ऐसे करके कॉलम n तक. ओके, सो यहाँ पर इनके पीछे वी हैव टू अरेंज टोटल नंबर एज 616. Okay, so let's say अपने पास n columns हैं. We can make n columns and n has to be maximized here कि highest column चाहिए हमें. ठीक है, तो 32 can be represented as n into some format q, and 616 can be represented as n into some format p, and n has to maximize, right? So means n is the HCF of these two numbers. So आप इनका HCF find कर लो, you'll get the n. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1. ओके, सो ये क्या बोल रहा है कि कोई भी पॉजिटिव इंटीजर का स्क्वायर आइदर इट विल टेक 3m और 3m प्लस 1 फॉर सम इंटीजर m. ओके, सो कोई लेट्स से 2 का स्क्वायर है 4. ओके, सो 4 कैन बी रिटन एज 3m in this format we can write, right? 4 5 का 5 का स्क्वायर विल इज 25 लेट्स से. ओके, तो 25 को अपन कैसे लिख सकते हैं? 24 plus 1, and this number can be written as 3 6 18, 3 7 21, 3 8 plus 1. इस फॉर्मेट में अपन लिख सकते हैं. सो यू कैन ट्राई विथ एनी पॉजिटिव नंबर, लाइक इट्स स्क्वायर कैन बी रिटन इन दिस फॉर्मेट. सो इन्होंने हिंट दिया लाइक हाउ वी कैन शो दिस और प्रूव दिस. सो लाइक लेट्स से एनी x be any positive integer and this can be written in this format. Like let's say we try to prove this using, so यहाँ पर any positive integer x can be written as 3q plus 1, 3q plus 2, given use Euclid's lemma to write it in this form. Like if you replace b with 3, so you can get this form number. So any integer can be represented as in this form. Now let's try to square each of them. ओके, इन सबका स्क्वायर लिख के देखते हैं. तो 3q का स्क्वायर क्या होगा? 9q स्क्वायर. ओके, एंड इसका स्क्वायर करके देखते हैं. 3q plus 1 का स्क्वायर करके देखते हैं. सो 9q स्क्वायर प्लस 1 स्क्वायर प्लस इन दोनों का 2 इंटू 3q इंटू 1, 3q इंटू 1 मीन्स 9q स्क्वायर प्लस 6q प्लस 1. अब इसका स्क्वायर करके देखते हैं. 3q प्लस 2 का स्क्वायर, सो इट विल बी 9q स्क्वायर प्लस 4 प्लस 3 to 6 to 12q. ओके, सो अपने पास अभी 3 नंबर्स आ गए हैं. 3q स्क्वायर कैन बी रिटन एज 3 into 3q square, and this will be any random integer m, so it can be written as 3m. okay, now इसको देखते हैं. इसमें को 3 से फैक्टराइज करने की कोशिश करते हैं. तो 3q स्क्वायर प्लस 2q प्लस 1, दिस कैन बी रिटन एज m, 3m प्लस 1. अब इसको देखते हैं. सो इसको देखते हैं यहाँ पर कैसे लिख सकते हैं. सो 3 कैन बी टेकन आउट समथिंग लाइक दिस. 3q स्क्वायर प्लस 3 4 जा 12, 4q, इसको 4q लिख सकते हैं. ओके, एंड 4 को कैसे लिख सकते हैं? 3 plus 1 लिख सकते हैं. सो ये कचरा हो रहा है, रुक जाओ, इसको रीराइट करते हैं अपन. 9q स्क्वायर प्लस 12q प्लस 3 plus 1 लिख सकते हैं इसको, राइट. 4 को 3 plus 1 लिख सकते हैं. देन आई विल ट्राई टू क्लब दिस इनटू वन थिंग, एंड इसको हम लिख सकते हैं 3 into 3q स्क्वायर प्लस 4q प्लस 1 प्लस 1, और दिस विल बी इंटीजर m, इसको 3m प्लस 1 फॉर्मेट में लिख सकते हैं. सो लाइक m इज एनी इंटीजर here, and like these are the square multiplication sum of integers will always be integer. So all see any number x integer can be positive integer can be written only in this form, and after squaring these numbers, like the x square, any like square of any positive numbers can be written into 3m, or 3m plus 1 or 3m plus 1. So all the squared positive numbers can be written only in two forms. Either it can take 3m or 3m plus 1. Hence we proved it. Similarly, you can prove this as well. You can again take 3q plus 1, 3q plus 2, and try to cube it, and then take 9 as a common factor between them, and those numbers will take this form. It will take only these forms. Cool. You can try to do that. The fundamental theorem of arithmetic. Let's come to the fundamental theorem of arithmetic. What it states. So what does it says? Any number can be written as the prime factor of some number. So let's say what's the definition of prime factor? Prime factor, what is the definition of prime number? First, let's see. So any number which has no other factor than 1 or itself. We cannot find any other factors. So 2, 3, 7, 11, 23. This number have no other factors. It has only factor itself or 1. So these numbers are called prime numbers, which has only two factors, 1 and itself. Okay. And all the other numbers are who has more than these factors are called composite numbers. Cool. By the way, there is a proof that the prime numbers are infinite. This is beyond our scope, but it is worth noting that if you try to keep on finding the prime numbers, right, it will never end. So it starts from 2 and the list goes on. So there is infinite number of prime numbers in the world, and this is very important property in forming that cryptography, and it is actually very important because all our modern system works on this, all the passwords and all this encryption, data encryption which is sent over internet uses this particular property, because it's very difficult to do the prime factorization of a number if it's a very big prime number, because there is computers can't do that fast enough. Let's say if I take very two big primes, number p1 and p2, and multiply it. Okay, to make it simple, let's take 7 and 11. P1 is 7 and P2 is 11. So if I multiply, 77 is the number. Okay, and to break it, what is the prime prime numbers of which it is made up of. So it's very difficult task for the computers if these two numbers are very big. Firstly, if I have to know if a number is given to me, let's say 1 1 3 2 a 1, this number, I am not sure whether this number is prime or not. So what I can do, I can try to find the factors of this number. So I can try to find the factors of, by checking by dividing it into by 2, 3, okay, 5. So I'll try to divide this number by 2. Since I know this is odd number, it will never be divisible by, it can be divisible by 3, it will never be divisible by 5. So we will be checking if this number is divisible by 2, 3, 5, 7, 11. If it is divisible, then this is not a prime number, this is composite numbers. So this important property where even computers find it difficult to break the number is used to do the cryptography. Like let's say I have an algorithm to encrypt a number, like given text, okay, and I have this number like flowing on the internet. Let's say this number is being transmitted, okay, 77. So anyone can see the 77, okay, but let's say the message is actual message is 11, okay, actual message is 11, but people are saying this message is 77, okay. So how people will decipher this message, the message is 11, if they can find, if they can find this number 7, if this can be written as 7 into 11, so people will know like this is the message here. So if I am a sender and I have chosen a key as 7 and receiver also has the same key 7, it's like lock and key system, okay. So receiver has the key and sender has the key 7. If I know one number which will divide this number, like okay, surely divide this number which is 7, then I can easily find the other number. So if I know 77 and if I have the key 7, I will know the other number 11, right? So we like what will divide this number? So like if it is like say p product of two numbers p1 and p2 which are very big number, let's say one like one prime number is very big, 2 1 3 5 6 7 8 9 9 1. So this is a big number, right? So computer has to search from all these numbers, like it has to go till here, till this point, because it won't be able to find any prime factor, because this number itself is prime number, so there won't be any factor. So it has to go there, and it will take computer to reach that stage, and it's very difficult task. So entire cryptography is based on this concept. It is beyond our scope, so we will not see. So one point to note is there are infinitely many prime numbers, okay, and uh, any uh, any composite numbers or any number can be written as a product of prime factors. Why this will happen? Why this will happen? Like let's say I am taking 30. 30 can be written as 15 into 2, okay, but again 15 can be broken down into some form, okay. Okay, so I'm trying to give the intention why all the numbers can be written as a product of prime factors only. So here 15 is not the prime number, 2 is prime number, but 15 is not. So 30 can be written as this, but even then like 15 can be broken into some factors of prime. Let's say if it can't be broken, means 15 doesn't have any factors. Let's say if a 30 is written as some number p into q, okay, p into q, this is p, this is q, okay, and p is not like we cannot break p into further prime factors. Q in let's say p into x into y. Okay, so there is no other factor of 15 which can be written into some factors like x into y. That means this number itself is a prime number. So if you continue the argument, so ultimately you will reach to the stage. If a number a is given, it has to be broken into some prime number p1 into p2 into p3 and goes on like pn. Let's say there is some number in between px which is not prime but composite number. So this composite number can be broken into some prime number x1 x2, right? Let's say if it can't be broken, there is no factor of this. If there is no factor of this, then px becomes the like prime number. So hope you get the intuition, like there is no other way. It has to be product of prime numbers only. So all the numbers in this world can be represented as a product of prime numbers. Okay, now the prime numbers can repeat. Let's say 9 we are taking. Okay, or in case let's say take 45 example. So this can be written as 3 into 3 into 5. So 3 square into 5. So these two prime numbers can be like clubbed together, and we can say, so we can state like it is not just product of prime factors. Like if we try to make it club the prime numbers together, it will be like powers of prime numbers, like product of powers of prime numbers, it can be represented. So this is the prime number and it will be unique. Okay, so that uniqueness is very important. So any numbers, if we try to arrange in ascending order, this number we can try to break into product of prime numbers. Okay, x y z something. Okay, so if x is less than y is less than z, this order will be unique. So there, like the same number cannot be broken into two sets of product of prime numbers which is not which is not unique. Okay, so that means like if you are trying to break the number, let's say take an example. I have a number and it can be prime factorized as x, y and z. Okay, and there is another number there is another prime factors z, p, q, r. We can take sorry. So a can be represented as prime factors of x, y, z. A can be represented of in the factor of p, q, r. Okay, so here if we try to arrange in this format like in ascending order, so x is less than y is less than z, x is less than y. So here I mean like x will be equal to p, y be equal to q and z equal to r. So this and this will be same, correct? This is the uniqueness of this prime factorization. So any number, like, you can try on your own. If you try to factorize those numbers, it will be unique. Okay, if you try to rearrange, so order doesn't matter here, the factorization is unique. This is very important property and it has very wide applications. So now let's suppose your collection of prime includes all the possible prime numbers. What is your cues about the size of the collection? Does it contain only a finite number of integers? No, there are infinite prime numbers. So if we combine all these prime numbers, is it possible with? So like again, like if you have infinite set of prime numbers and you take any n prime numbers and try to multiply them and with itself any number of times, it will keep generating composite numbers, right? Multiplication of any two prime numbers, like 3 into 3 is 9, that is a composite number. So there is infinite let's say there are infinite composite numbers. So there is infinite prime numbers, so you try to multiply prime numbers among themselves, you will end up generating a composite number. Cool. So here they are trying to explain, like, given a number, you try to find the factors of this number. So keep on dividing by 2, 3, 3, 3, and like it has generated this number. Okay, is the product of powers of prime. So let us try another number. So this number can be written in format of this number. So why we are not able to further break down this number and this number? Because this will be prime number, so there are no factors, but this number is the factor of like the prime numbers. So this leads to a conjecture that every composite number can be written as the product of powers of primes. In fact, this statement is true and called the fundamental theorem of arithmetic. Because of its basic crucial importance to the study of integers, let us formally state the theorem. Every composite number can be expressed as product of primes, and this factorization is unique apart from the order in which the prime factors occurs. So we have discussed this, and this is very important theorem to note, and it's called a fundamental theorem of arithmetic. Okay, so there is a brief and historical note about this mathematics. Carl Friedrich Gauss, he is referred to as Prince of Mathematics and one of the three greatest mathematicians of all time. Others are known as Archimedes and Newton. Archimedes and Newton. And composite numbers can be again, the fundamental theorem says that every composite number can be factorized as the product of prime numbers. Actually, it says more, there is just a unique way. Correct, we have discussed that. So 2, 3, 5 same, the product of this is same as 3, 5, 7, 2 or any other format. The prime factorization of natural number is unique except for the order of its factors. Yes. In general, given a composite number x, we factorize it as x equal to p1, p2, pn, where p1, p2, pn are primes and written in the ascending order. If we combine the same primes, we'll get power of primes. For example, this. So we are trying to combine the same prime numbers, and we can write as a power of prime numbers. Okay, so there is a question here. Consider the numbers 4 raised to power n. N is natural number. So n is natural number. Check whether there is any value of n for which 4 power n ends with digit 0. So हमने देखा है like any number to end with digit 0, like any number, कोई भी number है, let's say I take a number A, and if it has a digit 0 in the x3, like अगर ये सारे digits हैं, if a number is of the form this, right, so I can easily write it as something like this, x3 into 10, करेक्ट. इस फॉर्मेट में अपन लिख सकते हैं. So any number which ends with digit 0, 4, 5, let's say 4, 5, 10. So this can be written as 45 into 10. Okay. So 0 अगर होगा कोई नंबर में तो we can easily write it as some multiple of 10. Cool. So we see like अगर हम इसको इस फॉर्मेट में लिख सकते हैं. So इसको let's say this number is called p. So p into 10 लिख सकते हैं हम, means p into 2 into 5 लिख सकते हैं, करेक्ट. So any number which is divisible, which has 0 or ending with 0 has to have factor of 2 and 5, correct. It has to have factor of 2 and 5. So यहाँ पर क्या बोल रहे हैं कि can 4 to the power n, can it end with digit 0. तो 4 to the power of n में क्या numbers होंगे, like if 4 to the power of n is natural number like 1, 2, 3, 4 goes and like let's say infinity. So इसमें क्या होगा, 4 in like n is equal to let's say 2, so this number becomes 4 into 4, correct. If n is 3, this number becomes 4 into 4. Similarly it goes on. And 4 को कैसे लिख सकते हैं, 2 into 2, और इस 4 को कैसे लिख सकते हैं, 2 into 2. So this is rewriting it as good as 2 power 4, right, power n, sorry. So it is like 2 to the power 2n. So अगर n 1 है means this can be written as 2 to the power 4. If n in 1s means repeat multiplied 2 4 times itself. If n is 2, n is then this becomes 2 to the power 4. If n is 1 means it becomes 2 to the power 2. If n is 3, it becomes 2 to the power 6. So multiply. So only prime factors of this number will be 2. Okay, there won't be any 5. But to make, from here we have seen like it has to have prime factors of 2 as well as 5. There should be at least one prime factor 5 for this. So that means this number will never have 0. So the only prime factors of 4n is 2. So the uniqueness of the fundamental theorem of arithmetic guarantees that there is no other primes in the factorization of 4 to the power n. So there is no natural number n for which 4 to the power n ends with digit 0. You have already learned to find HCF and LCM of two positive integers using the fundamental theorem of arithmetic in earlier classes without realizing it. So like earlier classes mein how do we find LCM and HCF? Like you find using prime factorization, right? Like you try to factorize both the numbers, rewrite it as a product of primes and try to take the common factors out. That is how we used to find HCF. Okay, so highest common factors, that is the meaning of HCF as well. HCF is also known as like GCD, common greatest common divisor. So you are trying to find greatest number, like divisor which divides both the number. So HCF is same as GCD, greatest common divisor. And LCM, like LCM का क्या मतलब होता है? What LCM means, like least common multiple. Okay, so given a number, let's say given a number P and Q, LCM of this number is, let's say, A. So we can divide A completely by P, we can divide Q completely by A. Okay, so let's try to understand using example. अगर let's say if I say what is the LCM of 3, 3, it will be 3. Okay, 40, 40, it will be 40. 8, 5, it will be 40. Okay, so here like I need to know a number. Which is divisible by both A and B. Okay, so let's say LCM of A comma B is Q, then Q is divisible by A, Q is divisible by B. Okay, but Q has to be least number. So given like 40 comma 40, if these are the two numbers, there is number 80 as well. Like 80 is divisible by 40, 80 is divisible by 40. Given the case of 8 and 5, 80. Okay, 80 is divisible by 8 as well as by 5. But 80 is not the least number. The least number is 40. So beyond 40, like there is no other number which is lesser than 40 and is divisible by 8 and 5. So here it is called the least common multiple. Okay, so when the numbers are same, it is very easy to find the LCM, right? Because 90 comma 90, I know like if this number is itself divisible by 90 and this number is itself divisible by 90, so इससे छोटा तो कोई number हो नहीं सकता, right? Like if I have to, so LCM will be multiple of this number, like both the numbers. So LCM of A comma B, इसका LCM क्या होगा? It can be of the form, some form A into P, or it can be form B into Q. यही फॉर्म हो सकता है LCM का. LCM ऑफ ए बी इक्वल टू A इंटू पी और B इंटू क्यू, कोई इसी फॉर्मेट में हो सकता है, लाइक वेयर A B P Q B Q आर इंटीजर्स. So let's say that means like LCM is a multiple of either A or B. So इसके multiples 90 से छोटे तो हो नहीं सकते, like it can be either 90, 180, 270, ऐसा हो सकते हैं. And if the other number is also same itself, तो उसके भी यही हो सकते हैं, तो लिस्ट कॉमन विल बी दिस. सो इट इज़ वेरी इंट्यूटिव इन केस द नंबर्स आर सेम. एंड एक इंटरेस्टिंग क्वेश्चन है. लेट्स से इफ number is, let's say, something like this 5 3, इस केस में 15 होगा. 13 11, इस केस में 13 into 11 होगा. 7 12, इस केस में 7 into 12 होगा. Okay, and 13 7, again 13 into 7. Like, why I am able to find the LCM so quickly here? Like, अगर दो प्राइम नंबर्स हैं, their LCM will be like product of that prime numbers. Why? Because अगर LCM of two numbers क्या होगा? LCM of two numbers, let's say A, B, ये क्या होगा? Like some multiple of like A into P, or it will be some multiple of B into Q. Okay, बट यहाँ पर अपन क्या करते हैं? Like 5 and 3. Okay, if we try to break this number, let's say I want to find multiple of HCF of 27 and 6. Okay, 27 और 6 का HCF निकालना है. तो 27 can be written as 3 into 3 into 3. 6 can be written as यहाँ पर इसको देखते हैं. 6 can be written as 3 into 2. यही दो फॉर्मेट हो सकता है where we can write like it's better to write in ascending order. 2 into 3, 27 is equal to 3 into 3 into 3. तो इसके कॉमन फैक्टर्स ये होंगे ये. ओके, अगर मैं यही 54 बोलता, इफ़ इट वाज लाइक 54, तो यहाँ पर 2 एक और आ जाता, 2 एक और फैक्टर होता, तो हम इस 2 को भी उठा सकते थे. तो दैट मीन्स कि कुछ कॉमन फैक्टर्स यहाँ से हैं, कुछ कॉमन फैक्टर्स यहाँ से हैं. तो A और B का LCM in this case 6 and 54 का LCM is some common factors into जो रिमेनिंग अनकॉमन फैक्टर्स हैं. इन दिस केस 3, और यहाँ पर 3 बचा है, 2 बार 3 बचा है, राइट. एंड सम कॉमन फैक्टर्स. ओके, ये कॉमन फैक्टर्स यहाँ पर जो कॉमन फैक्टर्स उनको एक ही बार लिख रहे हैं, 2 into 3, और ये अनकॉमन है, सो वी आर टेकिंग दिस आउट. 3 into 3 into 3. ये कॉमन फैक्टर्स अनकॉमन फैक्टर्स का मल्टीपल हो गया. ओके, एंड why this will be LCM? Okay, now let's say this will be LCM because if LCM is a number which has to divide both, it has to divide 6 as well as 54. so 6 कैसे बना है? like 6 is made up of this number, right? and 54 कैसे बना है? this is made up of this number, 2 into 27, like 3 raised to power 3. so अगर ये नंबर 6 से डिवाइड हो रहा है, सो इट हैज़ टू डिवाइड बाय दिस एंड दिस. तो इसका जो कॉमन फैक्टर्स है दैट हैज़ बीन टेकन हियर. ओके, एंड 54 को डिवाइड करने के लिए this entire number has to be divisible by this number 2 into 3 into 3 into 3. तो 2 into 3 तो यहाँ पर कॉमन हो जाएगा, बट 3 into 3 नहीं हो पाएगा. ओके, आई हैव टेकन एक्स्ट्रा 3 here, so this is combined, so it will be just 3 into 3. This won't be there. So 2 into 3 कॉमन फैक्टर्स जो है इधर का और इधर का उसको डिवाइड कर लेगा. बट अगर मैं ये नहीं लेता, ये अनकॉमन फैक्टर नहीं लेता, ओके, तो 54 विल नेवर डिवाइड दिस नंबर. लेकिन जो नंबर है विल नेवर डिवाइड, बिकॉज ये जो कॉमन फैक्टर्स है ये तो चले जाएंगे इधर, बट ये नंबर्स नहीं जाएंगे यहाँ पर. सो लेट्स से इफ़ इट वाज नॉट 6 बट 30, 5 मल्टीप्लाई कर देते हैं, इट वाज 30 और 54 का देखते हैं. तो 30 और 54 का क्या होता? 30 could be written as 2 into 3 into 5, okay, and 54 can be written as 2 into 3 into 3 into 3. अब इनके बीच में अभी भी कॉमन तो यही दोनों हैं, ठीक है. तो ये नंबर्स एक बार उठेंगे, और ये एक बार इसलिए उठा रहे हैं क्योंकि इसके फैक्टर्स ये हैं, इसके फैक्टर्स ये हैं. अगर जो हमारा एलसीएम है, ठीक है, ये लिस्ट होना चाहिए, राइट, लिस्ट होना चाहिए सच दैट इट इज़ डिविजिबल बाय 30 एज वेल एज 54. सो अगर ये एक ही बार उठ रहा है कॉमन फैक्टर्स, तो दिस नंबर कैन इजीली बी डिवाइडेड बाय दिस. 2 3 को सेम रखेंगे एंड अनकॉमन फैक्टर्स को 5 3 into 3 कर सकते हैं. नाउ आई वांट टू टेस्ट कि 30 से डिविजिबल है कि नहीं. दिस एलसीएम शुड बी डिविजिबल बाय 30. तो 30 से डिविजिबल, तो ये कॉमन फैक्टर्स तो इजीली डिवाइड हो जाएंगे. अगर मैंने 5 नहीं लिया होता यहाँ से, ये अनकॉमन फैक्टर यहाँ पर नहीं होता, तो ये नंबर कभी भी 30 से डिविजिबल नहीं होता, बिकॉज कॉमन फैक्टर्स तो इसके आ जाएंगे बट 5 नहीं आएगा. तो 5 को हमें लेना पड़ेगा. तो ये नंबर प्लस ये नंबर विल डिवाइड दिस नंबर. कूल. और लेट्स से टेक द एग्जांपल ऑफ 54. ये कॉमन फैक्टर्स तो एक बार लिया है, तो अगेन ये एक बार तो डिविजिबल हो जाएगा, बट ये 3 into 3 यहाँ हमें लेना पड़ेगा, देन ओनली इट विल बी डिविजिबल. तो इफ़ यू नोटिस वेरी केयरफुली, ये क्या हो रहा है, लाइक आई एम ट्राइंग टू टेक दिस नंबर, लाइक 30 into 54 को हम लिखते हैं, तो कॉमन फैक्टर्स को एक नाम दे देते हैं HCF. ओके, सो HCF into अनकॉमन फैक्टर्स विच इज़ 5 here. ओके, एंड 54 को अगेन कॉमन फैक्टर्स को एक नाम दे देते हैं HCF. So it is same value, like this HCF and this HCF has same value. Of course it is same. So HCF into 9. Okay. And LCM क्या है यहाँ पर? LCM क्या है? ये नंबर. सो LCM को कैसे लिख सकते हैं? HCF into 5 into 9. सो यहाँ पर आप ध्यान से देखो तो ये क्या हो रहा है. आई कैन रीअरेंज दिस नंबर्स. सो प्रोडक्ट ऑफ 50 into 54, okay, is equal to HCF into HCF into 5 into 9. Okay, so product of two numbers A into B is equal to HCF into, ये this is same as LCM. तो यहाँ पर हम देख रहे हैं लाइक प्रोडक्ट ऑफ टू नंबर इज इक्वल टू HCF into LCM. So again, like if we know HCF and of a two number A and B, we can easily find LCM as A into B divided by HCF of those two number. और ये HCF हम यूक्लिड्स डिवीजन एल्गोरिथम से फाइंड कर सकते हैं. So this way we can easily calculate the LCM of number as well. And this is like the formal definition. Product HCF is the product of smallest power of each common prime number, numbers in factors in the number, product of greatest power of each prime factor involved in the number. So like HCF find करना हो तो you try to take as many factors out and try to club together. That becomes your HCF. And like smaller, like product of the smallest power of each common prime factors in the two numbers. Like let's say two numbers has, one number has some power something like this, 2 power 3 into 3 power 4, and another number has something like 2 power 1 into 3 power 6. तो इसमें से क्या मतलब हम एक ही बार 2 बाहर ले सकते हैं, राइट? 2 ले सकते हैं, 2 पावर 1 ही ले सकते हैं. एंड इसमें से भी हम लाइक 3 पावर 4 ही ले सकते हैं, 3 पावर 4. लाइक दो 3 यहाँ पर बच जाएंगे, 3 पावर 2 विल रिमेन हियर. ओके, so this is what it means like in HCF. And similarly the product of greatest power of each prime factor involved in the number for LCM. Now let's see some examples here. Find the HCF of by prime factorization method, hence find their LCM. So 96 can be written as this 2 power 5 into 3, and 404 can be written as 2 power 2 into 101. The HCF of two integers is like common factors should be taken out, which is like 2 to the power 2, 4, and LCM is like product of these two numbers divided by HCF. So this will be LCM. Very clear here. Find the HCF of HCF and LCM of these two numbers. Find the HCF and LCF of 6 and 72 and 120 using prime factorization. Okay, so here they have given three numbers, and three numbers can be rewritten as like factor product of prime factors, and then we try to take the common multiples out. So here in this case, if you see, it's 6, and once you have taken these numbers, like LCM will be the remaining numbers. So LCM के लिए क्या होगा, like highest powers को तुम्हें साथ में लेना होगा. So here 2 raised to 3, 2 raised to 3, and 2 raised to 1. So if we take highest power like 2 raised to 3, so obviously ये दोनों easily divide हो जाएंगे. 2 and 2 raised to 3 will go with this, and let's say we take 3 raised to 2 here. So जो दूसरे नंबर्स में जो इसके मल्टीपल हैं, that will easily divide that, correct? So this is also very intuitive, like we have to take the highest powers for LCM. Express each number as a product of prime factors. Like we can start dividing these numbers by 2. We keep on dividing until it is divisible by 2, and then move ahead with 3, 5, like this. We have to check and like easily express these numbers as the product of prime factors. Find the LCM and HCF of the following pairs of integers and verify that. So cool. Like again we can find the LCM and HCF and then check whether the multiplication of LCM and HCF is equal to the product of numbers, and it should be equal. Find LCM of the following integers by applying the prime factorization method. Again, like to find HCF, take the least common power factors and multiply them, and similarly for LCM, take the highest powers and multiply them. Given that HCF is 9, find the LCM. LCM के लिए क्या करोगे? We will multiply these two numbers and divide by HCF, which is 9. Check whether 6 power n can end with the digit 0 for any natural number n. So 6 का क्या factor होगा? So 6 will have 2 into 3. So this number can be अच्छा इसका लिख देता हूँ मैं, like इसको कैसे solve करेंगे? 306 into 657 divided by 9 will be LCM. Okay. एंड इसमें इसको कैसे लिख सकते हैं अपन? 6 का फैक्टर्स क्या है? प्राइम फैक्टर्स 2 into 3 है. इट इज़ लाइक 2 into 3. तो इसके पावर n, सो दिस कैन बी 3 power n 2 power n. So only prime factors it will have will 3 and 2. It will never have 5 as a prime factor, so it will never end with 0. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 plus 5 are composite numbers. Okay, so let's take 13 out of this. Like this can be easily rewritten as 13 into 11 plus 1. So there is one factor of this number called 13. So this number can be expressed as 13 into some number. So this is not a prime number because it has one factor 13, and again 5 can be taken out here, right? So this number has a factor of 5. So this is again composite number because prime numbers don't have like factors other than itself and 1. There is a question called circular path around a sports field. Sonia takes 18 minutes to drive one, and Ravi takes 12 minutes. Suppose they start at the same point and at the same time and go in the same direction. How many minutes they will meet again at the starting point? Okay, so this is a good question. Let's say given Sonia and Ravi and a track, circular track. Okay, so let's say this is the starting point. Okay, and they start in the same direction, Sonia and Ravi. So Sonia takes I guess Sonia takes 18. Sonia takes 18 minutes and Ravi takes 12 minutes. So Sonia takes 18 minutes, Ravi takes 12 minutes. तो इसका क्या मतलब है? Sonia after 18 minutes she will be back on the start position. Okay, this is start, and Ravi also goes here, and in 12 minutes he will on the start positions. Okay, so अपन देखते हैं कि स्टार्ट पोजिशंस पे कौन और कब कब रहेगा. सो 0th minute पे both let's draw on kind of number line here, and this is start positions 0. So Sonia and Ravi both are here. Okay, and this is like timeline, increasing timeline. So there is 12 minutes, 24, 36 and so on. 36 के बाद 48 I guess, yes. And then there is like 18, then there is 18 plus, okay, so it takes 18 minutes, right? So next यहाँ पर 36. So you can see here, right, कि Sonia will come back again at this position after 18 minutes, and then she'll take another 18 minutes to come back here. So she takes like 0, 18 and 36. At this time she is on the start position, and Ravi is on the start position at 0, 12, 24 and then 36. So Ravi ने कितना राउंड लगा लिया? Sonia has taken 2 rounds and Ravi has taken 1, 2 and 3 rounds. तो रवि 3 और सोनिया 2 राउंड के बाद they are back again on the start position and they both have taken 36 minutes. So this is like classic example of finding LCM of two numbers. तो 12 का 2 into 3 लिख सकते हैं, 18 को 2 into 3 लिख सकते हैं. Okay, so let's say now we have the choice, like 12 can be written as 2 to power 3 power 1, 18 2 into 3 power 2. इसका हाईएस्ट ले लो, इसका हाईएस्ट ले लो 3 का, तो 4 into 9 that is 36. Or you find the HCF of these two number, and like 12 into 18 divided by HCF, and HCF is what we say HCF, 2 एक बार आएगा and 3 एक बार आएगा, तो 6 to the 12. So HCF will be 36 here. You have many ways to do this. Hope this is clear. Like, how do you find revisiting irrational numbers? Okay, so what are irrational numbers? Okay, recall a number S is called irrational if it cannot be written in the form P by Q. Okay, where P, Q are integers and Q does not equal to 0. So irrational numbers cannot be written in form of P by Q. So here we know like root 2, root 3, root 5 are irrational numbers. Pi is also irrational number. And again, like here they are making a general statement called, if P is a prime number, then root P is always irrational. How we will see this, the proof we will see now. So yeah, pi, here they have mentioned it's irrational number. Like pi again has very great significance in mathematics, but we will not discuss, like it's not possible to state the proof of irrationality of pi in this scope. Like we cannot prove that this is pi is irrational because it requires higher mathematics, but we can easily prove these numbers are irrational numbers. And to prove root 2 is irrational, we have to we have to go in 2 stages. First we have to prove another statement. So in order to prove that 2 is irrational number, we have to see this statement. And what this statement says, by the way, like if you have noticed, like we have made a general statement, root of P will be irrational. irrational where p is prime number, and let's see like how we can prove this. So before moving that, we have to prove this statement. Okay, let p be prime number and p divides a square, then p divides a, where a is a positive integer. Okay, so ये क्या बोल रहा है? If p is prime and a square is divisible by p, then a is also divisible by p. We have to prove this. So let's say let's say 9. Okay, a equal to 3. Well, a equal to 3 and p is equal to 3. Cool. So if 9 is divisible by 3, a square, like a square is divisible by 3, then 3 is also divisible by 3, like a is divisible by 3, so it holds true here. Okay, now let's take another example. 15 square 225. If this number is divisible by, let's say, some prime number 5, if this is divisible by 5, then it is also divisible by root of this 5, and we can say this is also true. But how do we prove it? Okay, so a can be written as some prime factorization of let's say pn1, p2, pn2, p3, n3. Okay, like a can be written in this format. Cool. Where p1, p2, p3 are primes and these are the powers of the prime. Then a square can be written as p1 to n1 into p2 to n2, p3, like similarly it goes pn to n, like instead of n I should take some x number x. Okay, px to n. Here, like instead of y, let's n, like okay, y. So yeah, it goes like p1, p2, p3 to px, and power will be some random numbers 1, p, n1, n2, n3, and y. Okay, so square of this a can be written as this. If we square, like if we square this, so what will happen? Like p1 n1 into p1 n1, so it is as good as writing p1 to n1, right? So if a number divides this number, like for simplicity we can remove this, like we can assume the, like let's not write powers here. So p1, p2, pn. Okay, this is like a, let's say if prime factorization of a has 2 into 2 into 2, something like this, into 3, or and goes on. So let's write it in this way only. Like we can always write it into this, like instead of writing 2 into 3, we can write in this format. Okay, powers are not important, so we can always break the powers and write into this format, like product of prime factorization. So a square can be always written as p1 square, p2 square, pn square. So what will happen here, like if the numbers are in this format, so it can be easily written as 2 square into 2 square into 2 square into 3 square, something like that, if we square the number. Cool. So till now you have understood like how we can reduce this. So given a square is divisible by some prime number px, okay, and px is prime number here, okay, and a square is divisible by this, that means there has to be some number px as well here, okay, px square as well, because if it is divisible by px, then px should be factor of this, px should be factor of this, correct, and px will be present in form of square here. That means we can write a square as a into a will be p1 p2 px pn into p1 into p2 px pn, correct, because since a square is divided by px should be factor of this, and px can be like this, a into a can be written as like this, so a can be written as p1 p2 px pn p1 p2 px pn. So this means a is also divisible by px because px is factor here as well. So this is the proof of the statement. Okay, so a is equal to p1 p2 p3, okay, not necessarily distinct, therefore a square can be written as like 2 times, we can see here it can be written as this, and then if p divides a square, that means like p is one of the numbers of this p1 p2 p3 because it is divisible by this, and since it is like square, and if we write a, it will be p1 p2 pn, and p divides a as well, correct. So we have proved, let's say if p is a prime number which divides some number which is squared, then it will also divide the square root of that number. P divides a square, then p divides a, we have proved that, because p will be the factor of a as well. Now let's try to use this result to prove root 2 is irrational. So how do we prove that root 2 is irrational? We have a technique called proof by contradiction. So we first assume something and try to build on that, and then arrive at a result which is contradictory to our assumption, okay, and that result is false, that means our assumption was false. So this is like this is called proof proof by contradiction. It is one of the famous methods to prove something in mathematics. So we take one assumptions and try to build logically on that, and when we while building logically we come up to the conclusion which is not true, that means our assumption was not true. Cool. So here let's say we assume that we want to prove root 2 is irrational. Okay, so what we will do, we'll first assume, let's say root 2 is rational. Let's assume if root 2 is rational number, so what will happen, root 2 can be written in form of r by s, because all the rational numbers can be written in form of p by q, where q is not equal to 0. So similarly it can be represented by r by s. And then what we can do, if r and s has some common factor, so any number, let's say any number, what we say, let's say 18 by 10. Okay, if we are representing any number by like this, we can always cut down the common factors. So this number can be represented by 2 into 9, 2 into 5, and 2 is common factor, we can remove this, and this will be 9 by 5. Okay, so that means like we have to express in form of r by s and then remove all the common factors, and the reduced expression should be like this. So 9 and 5 are called co-primes. Okay, they are not prime numbers themselves, but they don't have any common factors other than 1. Such numbers are called co-prime numbers. Okay, they don't have any common factor other than 1. So we can easily represent root 2 in form of r by s, where r and s are co-prime number. Okay, so like they have represented by r by s, and then they are telling ki cut down all the common factors, and it can be easily represented by root 2 as a and b, where a and b are co-prime numbers. Cool. So root 2 can be represented as a by b. A and b are co-primes, like they don't have common factors other than 1. Cool. Now let's try to square this number, like this can be rewritten as root 2 b and equal to a. Square both the sides, 2b square equal to a square. Cool. So here you see 2 divides a square, because a square can be written as 2 into b square. So 2 divides a square, and we have seen in the above proof, above statement, if this is prime number, like p is prime number and p divides a square, p divides a, and in this case 2 is prime number, so 2 divides a square, because a square has a factor 2 here. A square is written as 2 into some integer b. Cool, because here a and b are integers, so this square will be integers. So a square has factor 2, that means a has factor 2. Now now we know a has factor 2, so a can be written in some form 2c. Cool. Now let's try to rewrite this root 2b equal to a into root 2b equal to 2c. Square it. 2b square is equal to 4c square. B square is equal to 2c square. That means b square is divisible by 2, means b is divisible by 2 using above statement, above proof. So 2 is factor of b as well, and we have already proved like 2 is factor of a. That means a and b have common factor 2. This means a and b were not co-primes, but we assume that it was co-prime, right? We assume that root 2 can be written as a by b and b are co-primes. So why this contradiction is coming? Like why this fact, like 2 is a factor coming of a and b? Because our assumption that root 2 can be written by some form r by s was wrong. That means root 2 is not a rational number. Hence we proved root 2 is a rational number. Cool. Now let's move ahead and see. Substituting again, like this is the same way we have done. Similarly, proof root 3 as irrational number. So again we will assume on the same line we will assume root 3 can be written by as a by b, where a and b are co-primes. Then we make we square both the sides. 3b square is equal to a square. Again, like 3 divides a square, means 3 is factor of a. Similarly, a can be written as 3c, so 3b square can be written as 9c square. So again, 3 divides b, like 3 is factor of b. 3 is common factor of a and b. The assumption was wrong. Similarly, like you can assume for you can continue and do for any prime number p, and you'll find like this way you can always prove that it has some common factor. The assumption was wrong and the number is irrational. Okay. Now there is another example to show 5 minus root 3 is irrational. So how we can prove that this is irrational? Okay, so let's assume this number is a rational number. So again it can be written in the form of a by b, where a and b are co-prime numbers and b not equal to 0. If we assume that, then rearranging the equation, like easily we can put 5 minus a by b here. And we have seen, like if a and b are integers, we get 5 minus a by b as rational. So you know, right, like if we try to multiply or divide any rational number with each other, the resulting number will always be a rational number. So we are doing same, like we are subtracting a rational number 5 by another rational number a by b, so resulting number will be always a rational number. Like why this is a rational number? Again, a rational number 5 is subtracted by a rational number a by b, means this is 5b minus a by b. Okay, so this can be written as like some integer and some integer, so where b is not what we say 0. So this is again a rational number because it can be written in p by q form. So again, like we have proved that root 3 is irrational number. So like this this is contradictory, right? This is rational and root 3 is irrational. We have proved root 3 is irrational, so there is a contradiction. This is not true. Why this is not true? Because our assumption this was a rational number was not true. So similarly on for other things as well, like you try to add any rational numbers or irrational numbers with some irrational numbers, it will be always irrational numbers. Like so it's like you add or subtract any rational number from irrational number, it will be always irrational number. And if you try to add two irrational numbers, it will be irrational numbers all. Now if you try to multiply also any irrational number with rational number, then the result product will be irrational numbers. I am stating rational with irrational. Okay, you don't multiply root 2 into root 2 because both are irrational numbers, so it will result to rational number like 2. So we have to multiply with irrational number with a rational number. So here again, like we have to prove 3 root 2 is irrational numbers. Again we assume the similar fashion. Root 3 into root 2 is a by b, and now we will have to rearrange root 2 by this, and again a and 3b is a rational number, like because again it is represented as p by q format, and 2 is irrational. We have proven that. So assumption this is rising a contradiction, so assumption is wrong. So similarly you can prove other things as well. Prove that root 5 is irrational. Again, like you can represent it in the form of a by b, and then try to prove like 5 is a common factor of a and b, and that is a contradiction. And similarly, if you are assuming 3 plus 2 root 5 as a rational, then you write it in form of a by b, where a by b are co-prime, a and b are co-prime numbers, and then rearrange those, and you show that root 5 is rational, but we have proved that root 5 is irrational number. Then 3 plus 2 root 5 is also irrational, and so similarly, like all these things can be proved using proof by contradiction. The method is same. Now let's go to the revisiting rational numbers and their decimal expansion. So any rational numbers, like any rational numbers, let's say given example 0.375, it can be easily written as this, like 375 divided by 10. So how much digits are there after point or decimal? We can easily divide by that. Okay, like one point is to note is, like after decimal, digit has some significance, 0, 8, but if you put 0 here, whatever number of 0 you have put here, it doesn't have any significance, but because the same number can be written as 1 2 3 4. Okay, so how many digits are there? 1 2 3 4, and this 4, 10 to the power 8. Okay, and this number can be written as 3108 into 10 to the power 4, 10 to the power 8. So it is as good as cancelling this, writing 1038 10 to the power 4. So only significance is of this, digit. You put n number of zeros after this. This is not significant, like it will always be cancelled out. Okay, so coming to the example again, any decimal number can be represented by in this form, and if you try to cancel the common factors from this and this, you will result into some form a by b, where a and b are co-prime numbers. So all the decimal numbers can be represented in a form a by b. Okay, similarly, like there are other numbers, like these are terminating numbers, so it is very easy to represent this, like, but there are some numbers like 0.3 bar. Bar means like this set of numbers will keep on repeating 0.33333, it will go till infinity. Okay, let's try to see like how we can represent these numbers in a fraction p by q. So see, rational numbers definition was it can be represented by p by q, where q is not 0, and if you try to represent in decimal numbers, it will either terminate like these numbers, or it will not terminate but it will repeat. Okay, it will repeat. So let's say assume take a number which is not terminating, 0.3 bar. So this means the number is something like this, it is repeating itself, 3 3 3 3 3 3 infinity, till it will go till infinity and keep on repeating. So let's assume this number as x, this number as x. Okay, so x is equal to 0.3333 till infinity. Now multiply x by 10, so it will become 10x, and it will be 3.333 infinity. Okay, so what is happening here? Okay, so we can easily multiply both the sides by 10, and this has transformed, like this will go till infinity. Now this is equation A and this is equation B. Try to subtract B minus A and it will give 9x equal to 3. 0. You are trying to subtract something like infinity by 0.333. So this is going till infinity, this is also going to infinity. This is same, right? This is same. So we can say these are the same number and it will become 0, like we are subtracting it. So result will be 3. So I am writing 3. That means 9x equal to 3, x equal to 3 by 9 equal to 1 by 3. So again we have represented this number in the form of p by q. And to see how this is working, like let's say I am trying to divide 1 by 3. So I put 0 here and multiply it 10 by 10. Okay. See, after putting decimal, I can keep on multiplying any number by 10. Again, like if this was the number, I can multiply it by 10 and divide by 10. Correct. So it is like 0.50. Sorry, like let me clear this. This is not the good example. Let's say there is number 0.5. Okay, it is as good as this number 50. This is same as this number. Cool. That's what we are doing, right? If I have to divide a number, let's say 5, okay, by 10, okay, so answer will be 0.5. But I can do the same thing. Instead of dividing 5 by 10, I can divide 50 by 100. Answer is still same. Now let's do something like this. 5 by 0.1. Okay, answer is 50. If I divide 5 by 0.01, answer is 500. But if I divide 50 by this number, okay, so now answer will be 50. So this number, so like in what I'm trying to say, like if I multiply by 10 here, I can easily use this like subtraction method. So I know, like if I want to divide 1 by 3, it is not going to be divisible because 1 is lesser than 3. So I put a decimal number here, and then I can easily extend it by 10. Now I know, like 3 will go here and 9 will be there, 1 will be remainder. Again I can multiply it by 10, and then again it will go by 3, 9. So this will keep on going, and we will end to infinity. So we can verify also this number is same as this number. So like this is the way you can find, like represent find the representation of p by q for this kind of repeating numbers. Now it can be anything, like 20, 34.3, 5, 6, 8, 7, 8, 7, 8, 7, 8, 7. So 34.56, 3, 5, 6, 8, 7 bar is there. Okay, this is the number. Now what you have to do is assume it x, then you have to eliminate this part, right? So what you can do, 1, 2, 3, 4, 5. So you can multiply 10 power 5 x with this. So what will it do? Sorry, like you need not multiply by 10 power 5, you just have to multiply by this 10 power 3. So 10 power 3 multiplication, what it will do, 3, 4, 3, 5, 6 dot 8, 7 bar will be the right. So you subtract 10 power 3x minus x with this number. So 3, 4, 3, 5, 6.87 bar minus this number. You subtract this number, okay. $34 like instead of doing this, like there is a better way to do this. Let's say I can represent this x as 34 plus 3.035687 bar. I can easily represent this, right? Now what I have to do is x minus 34 is equal to 0.35687. 35687 bar. Cool. Now you multiply this by 1000. Okay, x minus 34 into 10 power 3. Cool. It what it will give? It will give something like this: 356.87 bar. And now you can do the subtraction. Like you can try to minus this number from that, and if you rearrange, like this number can be easily proven as like some factors of p by q, and x you can find here, again some rational number p by q. Now let's move ahead. Now what does it say? Like if a number is terminating, right? If a number is terminating and non-repeating, so any non-repeating numbers can be easily expressed as a denominator of power of 10, correct? So denominator is always of the form, here denominator like p by q, right? So q is like 10 power n. Okay, so q will be 2 power n into 5 power n. Okay, so even if there is some common factor, if it is not co-prime, we can make co-prime, and co-prime can be made only by cancelling some powers of 2 or 5, right? So still there will be denominator will be of some power p into some power of 5 as q, where here p and q can be 0. Let's say there is a number 4 and we had something like 10 here. So 10 can be represented as 4 divided by 2 into 5. Now here 2 has only one power, right? Or like for better understanding, let's take 4 by 100 example. Okay, so 4 by 100 means 0.04, which can be represented as 4 by 100. That means 2 square by 10 square equal to 2 square by 2 square into 5 square, because 10 is 2 into 5. So this can be cancelled, but what I'm telling, denominator q is still of the form 2 power p 5 power q. If the number is such, then p will go to 0. That means 2 power 0 into 5 power q, and 2 power 0 means 1 into 5 power q. So always in a terminating decimal number, our denominator will be of the form 2 power q 5 power, like 2 power p 5 power q, where p and q can be 0 1 2 3 4, like any number, but it can be 0. So let's say there is a number x by 2 into 2. I can say this will terminate. This will always terminate. Why? Because I can rewrite this x into 5 into 5, and here 2 into 5 into 2 into 5 means x into 25 will be 10 into 10 will be 10 square divided by x into 25. So again, like, it is like dividing by 100. Similarly, if I have 5 cube into 2 square by some number x, this will always terminate because I can multiply here. So x can be written like this, number can be written as 5 square into 2 square into 5. Cool. So this is like 10 square into 5. So this number can be written as x into 2 into 10 power 3, because you multiply 2 here and 2 here. So this will always terminate. So that means if a denominator has only factors of 2 and 5, it will always terminate. And apart from 2 and 5, let's say a number, a denominator has something like this: x 3 into 7 into 5 into 2. So x can be 10 into 3 into 7. Here you cannot multiply this number, like let's say 3 by any number, 3 and 3. It will never make 10. So any number, if there is even a single factor in denominator which is not 2 or 5, this number we cannot write into form of like 10 to power some number y. If we cannot write, like, this will never terminate. But since we are able to write in the form of p by q, we know it's rational numbers. So even though it will not terminate, but it will start repeating at some point. Then only we can write some decimal representation of that. It will start repeating. And we know, like, let's say if we are representing some number like this, and let's say there is 7 by not 5, let's say take 3. So let's try to divide this 7 by 3. 7 2 just 6. 6 is gone, 1 is remaining. Now 1 is less than 3, so I will put decimal number here and divide by 3, and 9. Then it will continue growing, like 2.3 bar is equal to 7 by 3. Cool. So again, like I had explained, like 2.3 bar can be written as 2 plus 0.3 bar. That means this number can be written as 2 plus 1 by 3. 2 plus 1 by 3. Correct? .3 bar. And I already shown like how we can convert this to this this number, correct? So like whenever you are given any number, like some number point, uh, some bar number 35 like this, so uh, let's say it is 24.35 bar like this. So you just find the decimal representation of this, and then you add that number to that decimal representation. So you can find 0.35 decimal representation and add 24 to it. This will be the fraction. So you try to write as p by q plus 24. This will be the fraction. Similarly, like if you want to write like 24.3835 bar is coming here. So this is as good as like 24.38 plus 0.0035 bar, right? So you try to write this number as fraction of p by q, and then you add this number 2438 by 100. So these are two rational fractions. You add them, it will be still a rational number. So we have seen like for a fraction to terminate, the decimal number has to be of the form 2 power n, 2 power m, and if there is any other factor than this, that number will never terminate. Like it can be written as p by q, but it will start repeating. Like after some time the decimals will start repeating, and that repetition will never have zero, uh, not zero. Like when I'm trying to divide this number, let's say any number 1 by 3, okay, so this remainder will never be 0. Remainder will never be 0 in such case. If you're trying to divide number of the form where q is not of the form 2 power m 5 power n, then this number will never terminate, but it will repeat, and this will start repeating like it can generate. Let me take some other example. Let's say I want to divide 38 by 7. So what we can do is 7 5 ja 35, and then 3 is remainder, point 7 4 the 28, 2 is remainder, 7 2 the 14, 6 is remainder, 7 7 9 63, 7 8 is 56, 7 8 into 7, yes, 56, 7 8 is 56, then 4, okay, 4 has come, then 40, 7 5 is 35, then 5 has come, 5 for the 50, 7 7 the 49, 1 has come, 10, okay, 7 1 the 7, 3 has come, okay, so now 7 for the 28, 28, then 2 has come, so 7 2 the 14. So if you observe here, so once we have got the same number as remainder, it will keep on repeating, right? Again, see, like I have started with 4 here, so we reached this point, right? Yeah, you ignore this and you focus here. 3 was remainder, then 4 was quotient, okay, we come to 28, okay, then 2 was remainder, and then we continued till this number. Cool. And after performing this many operations, again the number has come to 3 as remainder. So if we continue this, again these are repeating, right? This is repeating, so it keeps on infinite loop. So it is repeating in this format, like 5 4 2 8 5 7 1. This is repeating. This entire number forms the bar, and you can notice now, like this will never end, because again this is forming the loop. Again this same numbers will come as remainders, and it will keep on going. So the point is, like this number had like what we were trying to do, 38 divided by 7. So 7 can, like, it is not of the form 2 power m or 5 power n, like, right? So there will be a time, like, so what are the remainders here? So 3 was remainder here, okay, then 2 was remainder, then 6 was remainder, then 4 was remainder, then 5 was remainder, okay, and then 1 was remainder, and then again 3 was remainder, again 2 was remainder. So if you see here what is happening, 3 2 6 5 4 5 1, these all numbers are smaller than 7, correct? All numbers are 7 like smaller than 7. Like obviously, like we are trying to divide by 7, the remainder cannot be greater than 7. Cool. And this remainder cannot be 0 as well, because if, let's say, if at some point remainder has become 0, that means division has stopped. So this will not repeat. Let's say it was after 2 the remainder was 0, means like it is dividing it and we cannot further proceed, then it is not repeating. So this number will be of some form, like this number plus this number, like something like 4 2 8 5 7 1 4 2. This is stopped, so it can be represented by this 10. So the point is, this remainders will be lesser than this number, and it will never be 0, else it will stop. So this is the theorem point, like this is the same problem we discussed, and it has been noted as a theorem here. So let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 power n 5 power m, where n m are non-negative integers. Non-negative, it is saying, means it can be 0. So this is the statement. This is very important thing to note. Like if you have to solve the questions or say any number, so I can say like any number 2 by 5, will it terminate? Yes, because it has only factor of 2 or 5. So 2 multiplied 2, 4 by 10, it will terminate. 4 by 7, it won't terminate. 4 by 13, it won't terminate. 4 by 8, now this is power of 2, so it will terminate. 4 by 26, it won't terminate, because this can be written as 4 by 2 into 13. 13 is prime number, and this is not power 2 power m 5 power n. So easily you can say which is terminating, which will not terminate. Again, like it is easy to represent as decimal. Like you just have to factorize. Like, let's say you have 5 power 4 factor, means you have to multiply it by 2 power 4 to make the group of 10, right? So 80 by 10 means this has factor like 2 power 4 by 5 power 1. So to make it like multiple of 10, 5 power 3 is missing here, so you multiply by 5 power 3 numerator and denominator. You will make the denominator as some power of 10. There is another theorem. Let x is equal to p by q and be a rational number such that prime factorization of q is of the form 2 power n m power 5 power m, where n m are non-negative integers, then n x has to be a decimal expansion which terminates. So it's like converse of the above problem statement. So it says like if p by q is terminating, then q will be of the form 2 power n and 5 power m, and here it's reverse. Like if it is saying p by q is a rational number and q is of the form 2 power n 5 power m, then it will terminate. So both is true. Converse is also true. And here we have seen the same example. So we can see like we tried to do the same thing here, and it started repeating after this, and it is also saying the same thing. 0 will not show up. Why? Because if 0 shows up, then it will stop. Remainder cannot be 0. And again, if it is not of the form, then again it will be it can be represented as decimal number, but it won't be terminating, and after some point it will start recurring. So that is the statement made here. Yeah, so it is telling without actually dividing and seeing the result, you have to say whether it will terminate or not terminate. So what you have to do, you have to just focus on the denominator. So here you can see like this in this example, you have to do the prime factorization of all these numbers. So here I see here like it's very easy. So 16 can be represented as 2 power 10 into 10 power 2 square. So like 0 can be easily eliminated, because again like 10 power 10 raised to any power will be some sum of 2 power n 5 power m, right? And this is again like this. So here you can see 2 power 4 means this can be represented n plus 4 into uh, 5 power m. So this will terminate. uh, this will not uh, okay. So let's see here. Okay, 6 by 15. So 2 into 3, 3 into 5. So you notice here, like here, even though there is 3 here, but these are not co-prime numbers. There is some common factor between them. So you cancel the co-prime numbers, like you make it in the form of co-prime. So actually this number uh, is of the form 2 by 5, and 5 is 2 power 0, 5 power 1. It is of the form 2 power n, 5 power n m. So this will terminate. Okay, 129 is prime no, not a prime number, sorry. So it is divisible by 3. So 3 can be written as like this: 3 4s are 12. Okay, 3 3s are, right, 3 4s are 12, 3 3s are, and 43 is a prime number, I know. So 2 square into 5 power 7, 7 power 5. So like this is fine, like this is fine, this particular is fine, but 7 power 5 is not fine. If it had some 7 power 5 here, or 7 pi more than 7 power 5 here, so this could have been cancelled. But since there is no 7 power 5 or more than that, this will never terminate. Okay, similarly you can see here as well, like 7 into 11. Here what we can see, you can easily discard this 0. So you have to test for this. 7 into 11 by 3 into 7, 7 7 cancelled. This is like 11 by 3 into 30, but 3 is still there, so it will not terminate, and it will be recurring. So similarly you can solve. This is very easy, like you multiply by 2, 70 by 100, it will terminate. The following real numbers have the decimal expansion as given below. In each case, decide whether they are rational or not. If they are rational and of the form p by q, what can you say about the prime factors of q? Okay, so this is terminating, right? This is terminating. So what about the prime factors of q? So prime factors of q will be 2 power m, 5 power n, of this form. This is, I think, this is actually not terminating, a non-repeating also. So this cannot be represented by in the form of p by q. And this is non-terminating, but it is recurring. So it will have uh, some prime factor in decimal, which is not 2 power m, 5 power n. So now let's move to the other section. So we are summarizing the entire chapter here. like what we learned, like we learned Euclid's division lemma, like any number can be written in form of this number, this expression. Given a number a and b, it can always be written in the form of this expression, and where the remainder is less than b. Then there is Euclid algorithm to find HCF. You find like HCF of a comma b is equal to HCF of q and r, and similarly you follow the process unless r becomes 0. In the step where r becomes 0, b will be our HCF or GCD. Then there is fundamental theorem of arithmetic, like all the composite numbers can be expressed as prime factors, like product of prime factors, and that factorization will be unique. And then we looked at the theorem called, if p is prime and divides a square, then p also divides a. We have seen the proof where a is positive integer. Then we have seen the way to prove root 3, root 2 as irrationals, and then we have seen like any multiplication or addition of rational numbers to irrational is also irrational. We have seen the proof as well. Then we have seen like if a decimal expansion terminates, then denominator will be of the form 2 power n to m to 5 power m, where n m and n m are non-negative integers. It can be 0, but and the converse was also true. Let's say if a fraction is given in form of p by q, and q is of the form 2 power n 5 power m, then the number will terminate. And if the q is not of the form 2 power n 5 power m, then it will not terminate and repeat. Like after some point it will start recurring. So this is the summary, and this is the note for higher classes, like LCM as product of LCM and HCF of 3 numbers does not equal to the product of 3 numbers, but the following results hold. You can try to find the intuition or like proof, like by expressing, like you can assume something like this, like p let's say the HCF of p q r is h. Okay, so you can try to represent p into some form of not like that, sorry. First you have to rewrite the like HCF of these two numbers. HCF of p q is h1, let's say. HCF of p r is h2. HCF of r q is h3. Then you can rewrite something like that. HCF of p q r is h4. That means like p will be something like h1 x1 of the form. Q will be something like h1 x2 form, and similarly you have to write this numbers as well in form of HCF. Okay, and then when you write as a product of these numbers, like you will realize like the LCM of this number has to be like a product of this number into HCF of this number. So this like this number is like it let's say there are common factors of PQ are is like P1, P2, P3. Okay. Okay, so like each number will have some prime factors like this. Cool. Q will have some prime factors like this. R will have some prime factors like this. Okay. So HCF of those numbers will have common factors from this. Common factors from this will be written here. There will be some common factors written here. But again, like HCF means LCM means like these numbers. Obviously, like if I am trying to find a LCM of this, so this is like my LCM. If this is my LCM, it will be easily divisible by P, Q and R, because it has some product like this. Okay. And if you try to multiply these numbers, then there will be common factors here between PQ, QR and PR. There will be some common factors here which will repeat, right? Which will repeat. So those common factors have to be eliminated. So that's why we are dividing the common factors of the pairs like individually. Hope you are getting, right? So LCM is the number, like let's say let me give example again. Let me try to explain. Okay, P, Q, R are three numbers. So if I say, let's say I want to find a number which is divisible by P, Q, R individually. So this number can be easily P into Q into R. Okay. This number can be easily P into Q into R. Okay. But this is not the least number, because let's say if P and Q have some common factor X, P and Q have some common factor X, so PQ can be written as X into some number Z1, so X Z1. Okay. And again, like there can be some common factors between Q and R, that can be X Z2, and there can be common factor between P and R as well, X Z3, and all these numbers can have some common factors X. So it can be again represented like X Y1 Z1, X Y2 Z2, X Y3 Z3. Cool. So X is common between all these numbers, right? So what can happen here? So X has to be taken out here, right? And these numbers can be represented here. X has to be taken out here, and X is HCF, like common factor between all the three numbers. This is HCF. Okay. But let's say these two numbers have some HCF, like h1, these two numbers have h2, and these two numbers have h3. So I am dividing by, like, let's say h1, h2, h3. Cool. So if I am dividing common factors of these two, okay, so I am cancelling all the factors, like of this number, okay. And if I am dividing by this two and this three, I am taking one of the factors which will be common between these two. That's why I have to multiply those common factors of all three again here. So that will be the LCM. If you try to do with number examples, you will get to know, like I can see 6, 8, 10. Let's say take example of this. So 6 will be 2 into 3, 8 will be 2 into 2 into 2, 10 will be 2 into 5, okay. So PQR, like 6, 8, 10, okay. It can be represented as 2 into 3, 2 into 2 into 2, okay, and then 2 into 5. If I have to find HCF of all three numbers, then I have to take the just common factors. In this case, the common factors of all the three numbers is 2. So HCF of this P, Q, R is 2. So I have written now let's take the HCF of two pairs, okay. So let me write HCF of this P and Q is 2. HCF of P and Q is 2. HCF of Q and R is 2. And HCF of this and this factor is 2. Okay, so 2 has taken common out here. Again I am taking one factor common here and one factor common here. So if we observe LCM of A 6, 8, 9, 10 has to be like uncommon factors, like highest power taken, like we have to take highest powers here. So highest powers here is like 2 3 times, sorry, this will be the highest power 2 3 times, and then 3 one time and 5 one time, 3 and 5 one time, okay. So if we want to take the product of like if let's say LCM of this three number is like L, then L has to be divisible by this number, and this number. Then we are trying to divide means L has to be divisible by product of this prime factors of this number, and this number, correct. So to 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 make the like to make this division possible, we are taking the highest powers of all the common prime factors. Because if let's say uh, uh, 2 power 8 2 power 3 we have chosen, so all the lower prime factors of which will appear here of 2 will be easily divisible by 3, because 2 power 3 will be divisible by 2 power 0, 2 power 1, 2 power 2, 2 power 3 easily. So all the lower powers will be anyway divisible. Correct. So that's why we are trying to eliminate the common powers of this. Like we are multiplying this uh, numbers, and we are trying to eliminate the common powers. Like these two common powers is like 2, so 2 is eliminated one time here. Okay, then this 2 has common power 2, so 2 is eliminated one time here. Okay, and then this 2 has some common powers, and that is eliminated here if we are dividing the HCF in pairs. So you notice here कि we have cancelled all the common factors one time more, right? It has been cancelled one time more. Like there should have been at least one power 2, and that 1 power 2 is like HCF of all these three numbers. In order to be divisible, it has to be one number from here, right? So that one number will come from HCF of all three numbers, and HCF all three numbers we are writing here. We have taken here HCF. Where is that HCF? Is this is 2. This will be taking here. So it's like we are taking the common factors from the two pairs at a time. That is actually cancel one more extra number one more time, so that extra number has to come from that common HCF. But this is not in the syllabus. I was just explaining to give the intuition why it is happening. So it can be generalized for 4 numbers as well. Like you just have to imagine, like you have to take like pairs of 3, pairs of 2. So it's like if you are cancelling by 3 in pairs of 3, then you have to multiply here, like which is like taken extra from here. So you have to multiply here in order to compensate, but that is not required, so we can skip right now. Let's end the session.